All right, so I'm going to present about the front-end web servers. That's the smuggling corridor. A quick 20 seconds about me. My name is Anuj Mistry. I'm a senior consultant with CGI for offensive security, and that's my Twitter handle. That's a big number. What does that number show? I wish. Any guesses? Number of attacks? No. It's 1.7 billion. I'll give you some hint. That's right. Those are the number of web servers in the world. 1.7 billion web servers in the world. 7 billion population, so imagine how many web servers are there. And to each user, this is what we see. End user and a web server. But in practice, that's not the case. There's usually an intermediate server. By intermediate server, it could be a cache, it could be a proxy, it could be a reverse proxy, a load balancer, any of those HTTP-enabled intermediaries. This usually between the front end and the back end server, just for performance reasons. They do not terminate the HTTP connection after every request. It's an active HTTP connection, the same connection that's being reused. Now, when the same connection is being reused, one challenge is to identify the boundaries of messages. How do we differentiate the length of each message, differentiate one message from the other? This is where we get an opportunity to attack the backend server whenever the front-end server and the backend server do not agree in terms of the implementation for the message length. When do we consider a message to be complete? When the connection is closed by the server. Some of the messages have an implied content length. The 204, 304 messages, they have 0 content length. So the front end and back end servers, they agree that, yes, this is the message length. So they can differentiate between different messages. A third method is the content length header. In the given example, content length is 5, so ABC, and then CRLF. So total 5 bytes is the content length. And another header called chunked encoding. Whenever we have transfer encoding header, the format is a number, the length of the data, and then 0 to indicate that that's the end of the message. It could be multiple chunks. First chunk is just 3 bytes, second chunk is 5 bytes, and then 0, which shows that that's the end of message. So like I said earlier, whenever the front end and the back end server, they do not agree on the same means to determine the end of message, we have an opportunity. Suppose the user sends a malformed request, which travels to the front end, which goes through the front end server, but then gets attached to the different request at the back end. This is what is request smuggling it's all about. I'll show you how to do it through an example. Suppose I have a setup with Sun1 proxy server. It's pretty old setup right now. Sun1 web server. The way they are implemented is whenever there are 2 content length headers in the request, the Sun1 proxy server uses the second header. It considers the second header as the length of the message, and that's where it discriminates the boundary of the message. The web server uses the first header that's mentioned. So what happens if we have 2 content length headers in our request? Here, if you notice, there's a content length header says 0, another one says 53. Let's see how this message flows into the front end server, which is the Sun1 proxy, and then into the web server. The front end server, the proxy, which considers the second content length header, will think this is the end of message, which means that's request 1, and the remaining is request 2. When this message flows onto the HTTP connection, which is kept alive, onto the backend server, now the backend server looks at content length header 1, this one, and it says length is 0. So this URLF, this is where the request ends. So this is the view of the backend server in terms of the messages. Now when you see the difference between how the front-end server views the messages and the backend server views the messages, it gives us this message from get to foo that's being smuggled into the backend server. I'll give you a moment to process this, because this highlighted request is being smuggled to the backend server without the front-end server knowing it. What are the implications of it? Typically, we encounter 4 different types of setups or environments. Some where both of them look at content length headers, but different ones. That's called the cl.cl, as we saw in the first example here. The second kind of setup is where the front-end server looks at the content length header, but the backend server looks at the transfer encoding header. The third kind of setup is the reverse, where the front-end server looks at the transfer encoding header, and the backend server looks at the content length. So here again, there's a mismatch in what how they are implemented in terms of marking the boundaries of messages. And the fourth one is when there are multiple transfer encoding headers, but then the front end and the backend server, they look at different ones. So these are 4 types of vulnerable setups that we'll encounter in the wild. Using these 4 setups or this technique, we can perform an HTTP request smuggling, as we saw in the first example, right? We smuggle a request from the front-end server to the back-end server without the front-end server recognizing it. We can even perform HTTP response smuggling. We can split the request, and we can split the response. So these are 4 different types of attack vectors using the HTTP desync methodology. We saw the first one already in an example, and I'll show you an example of the last one, that is HTTP response splitting. How do we force the backend server to spit out 2 different responses after sending just one request? Simple example, front-end server sends a message to the backend server, and we make the backend server send out 2 different responses. Let's see how this can be exploited. This can be exploited when any application embeds user data into a response header. And we'll see an example how this can be accomplished. Suppose I have a site where normal request to the index.php page says this, and the response, this is the user request, and it's embedded into a header in the response. This is gold for ethical hackers, right? Here, the user input is the country code, which is Canada. What if, as an attacker, I change the user input to add some more headers and some more headers? So for the request, this entire is a request. We are sending one request to the backend server. While sending, practically, I need to URL encode it. So this is how it looks. The request is a single request with this malformed data being sent to the backend server. The backend server will spit out 2 different responses. One for the first request that we saw. The second one would be the 200 OK request. So one request going out, 2 responses coming back. This is how it looks. So the user is sending just one request. There are 2 responses being sent back. Now the front-end server will queue up this response, the response 1B, and it will reply that to the second request. Now, how this can be exploited is when a user so this is user 1, and suppose a different user is going to use the application. So different users of the application, we can, as an attacker, we can force a response to the different user through this technique. Just putting it all into one picture so that we know how it works. Just one request, 2 different responses coming back. The impact, whenever there's a vulnerability of which you can exploit, you have to look at the impact. One impact is web cache poisoning. So most of the front-end servers also implement caching, and we can have a result of a web cache poisoning, which means on Facebook, for example, our login page, if we poison the cache to respond with a logout, any of the users which try to go to the login page, they'll be redirected to the logout page automatically. This is a temporary attack because then whenever the cache is purged and then it's built new, the application works normally. Another kind of attack is the response hijacking. So we can hijack the response from a backend server, which enables us to steal a lot of data. Any additional headers from the front-end server that are being added, any session cookies that are being added by the front-end server, we can basically ask the backend server to spit it out to us. It's possible to deface a website, which has business impact in terms of the commercial and the in the image. It's possible to bypass any of the security controls on the front-end side. So it's possible to bypass any web application firewalls, next-gen firewalls, network firewalls, IPS, IDS systems using this technique. And it's possible to steal credentials. Just like we said, we could make the backend server spit out additional responses. So we can make the backend server spit out credentials of other users to us. So credential stealing. Now we can see that all these different types of possible attacks using this technique are very severe. They're very critical. This is a very small list of the systems that are vulnerable. Most of these are, actually all of these are now patched. But this is only a very small number. Recent researchers have seen that any new field that they go in, any new target they attack, they do have these kind of vulnerabilities. Seeing the vulnerabilities, what are some of the steps the blue side, defensive side can take in order to remediate this vulnerability? It's usually multi-layered. The first one is that application layer, where whenever there's a web app, the backend server, they have to sanitize everything. Any user input, special characters, CR, LF, everything has to be sanitized. So very strict input sanitization has to be implemented. Avoid using single session NTLM HTTP auth. Use Kerberos instead, which is more like a ticketing-based auth. At the intermediaries level, which is most of the front-end servers, the load balancers, cache servers, all those vendors, they need to drop or fix bad data. When there's bad data coming in from a user, either fix it or drop it. They need to be very strict in terms of implementing the RFCs, specifically 2616. Any deviation from RFC and then the front-end back-end server, they will have disagreements in terms of the length of the message, and that's gold. Use HTTP2 towards the backend, which has a much stronger implementation, and also disallow trace methods if possible. The frameworks which are used, just do not embed any bad data into the responses. That's how you remediate on the framework level. Just a quick recap. So HTTP desync vulnerabilities are critical, and they're widespread. There are 4 different kinds of setups or environments that we usually encounter. The attacks that are possible are 4 key kinds of attacks, and remediation is always multi-layered. There's no just one fix. It has to be at each layer, at the front-end server, the application layer, the framework layer. That's a way to remediate such attacks. A huge credit goes to Amit and James. Amit he's the one who originally did a lot of research back in 2005, and then after that it was kind of forgotten. And James Carroll from Porttrigger recently did a very good research. He's developed a methodology to detect, confirm, and then exploit these vulnerabilities. And he even added a small add-on onto Burp Suite to test for desync attacks. So shout out to Amit and James, and thank you so much. I'll leave. Thank you. Thanks. While taking questions, I'll leave this on just for recap. Yeah.
Any questions?
No? Okay.
Well, thank you very much. And A token of our appreciation. Thank you very much.
So much. Bye.